Hello everyone. In the previous video, you have learned how to approximate the distribution of a statistic by means of the parametric bootstrap. This is a resampling scheme where new datasets are generated from an estimated parametric distribution, which are then used to compute realizations of the statistic of interest. In the previous video, this was possible because in the statistical testing problem at hand, the model distribution under the null hypothesis was assumed to be an exponential distribution. However, there are situations in which there is no reason to assume a specific type of distribution for the dataset at hand. In such cases, the parametric bootstrap cannot be applied. In this video, you will learn an alternative resampling scheme called the empirical bootstrap that can overcome this difficulty. Let us return to the video 4 of week 3, where we compared the height-width ratios in the works of art of Shoshone Indians with the golden ratio 0.618, which is the typical ratio used by the ancient Greek. The observed ratios are modeled as realizations of independent random variables x1 up to xn with mean mu. The parameter mu then represents the expected height-width ratio in Shoshone rectangles. We want to test the null hypothesis that mu is equal to the golden ratio against the alternative that it is greater. As test statistic, we use x bar minus 0.618 divided by Sn over square root n, where x bar and Sn are the sample mean and sample standard deviation of the xi's. Now the value of the test statistic for the dataset is 2.053. This is clearly larger than 0, and as such, it is in favor of the alternative hypothesis. But the question is whether it is large enough to reject the null hypothesis. In order to decide this, we want to compute the right-sided p-value. But for this, we need the distribution of the test statistic under the null hypothesis. Now recall that under the null hypothesis, the test statistic is equal to the studentized mean. The name refers to the fact that if the ratios can be modeled by a normal distribution, then the studentized mean has a student t distribution with n-1 degrees of freedom. However, the assumption of normality is questionable. This can be seen from a normal QQ plot, where the point seems to deviate somewhat from a straight line. This is also confirmed by the Kolmogorov-Smirnov goodness of fit test for normality, which we discussed in the previous video. Testing the null hypothesis that the distribution of the ratios is some normal distribution gives approximated p-value of 0.018. Now, an alternative might be to use a large sample approximation for the studentized mean on the basis of a variation of the central limit theorem. But again, this is also questionable since the sample size is only 20. Now, a resampling method can be of help to approximate the distribution of the studentized mean. For this, we must be able to generate a new dataset from some estimate of the model distribution. Compute the value of the studentized mean, where mu hat denotes the expectation corresponding to the estimate f hat for capital F, and repeat this a lot of times. But there is no reason to choose a specific type of distribution, so we cannot model the data by some parametric distribution, estimate the parameter, and then generate the estimated parametric distribution. However, you have already learned an estimator for the model distribution that does not assume any specific parametric type. Do you remember which one? Indeed, the empirical distribution function Fn. Now here's the graph of Fn for the 20 Shoshone ratios. It lies between 0 and 1, and it has a jump of size 1 over 20 at every observation. Now, how do we generate a new dataset from this? To understand this, let us illustrate the analogy with generating from a discrete distribution. Consider a random variable x with a binomial distribution with parameters n equal to 3 and p equal to 1/2. Then x has possible values 0, 1, 2, and 3, with probabilities 1/8, 3/8, 3/8, and 1/8. The distribution function F of x at a point t is the probability that x is less than or equal to t. So, f of t is equal to the summation of the probabilities of values a that are less than or equal to t. Now here's a graph of the distribution function of x. It lies between 0 and 1. It has a jump of 1/8 at 0, additional jumps of 3/8 at 1 and 2, and an additional jump of 1/8 at 3. Now this means that from the graph of the distribution function, we can extract what are the possible values for x and what are the corresponding probabilities. Indeed, the possible values are exactly those values on the horizontal axis where the graph has a jump, namely at 0, 1, 2, and 3. Furthermore, the size of the jumps are precisely the corresponding probabilities, namely a jump of 1/8 at 0, jumps of 3/8 at 1 and at 2, and a jump of 1/8 at 3. Now here is the empirical distribution function of a data set with 4 elements, say x1 up to x4. And suppose for simplicity that the elements are ordered. It looks almost the same as the previous graph. It lies between 0 and 1, and it has a jump of 1/4 at each element of the data set. Now, if this was the distribution function of some discrete random variable, x star, then in the same way as in the previous case, we can extract from the graph that x star has as possible values the elements of the data set, with equal probabilities 1/4. So we conclude that if we want to generate a single number from this empirical distribution function, this is equivalent with drawing an element of the data set with equal probability 1/4. In general, if we have an empirical distribution function of n points, and we want to generate a single number from Fn, this is equivalent with drawing an element of the data set with equal probability 1/n. Well, we can do this by means of the function the R function sample. If we want to generate a new data set of size 20 from the empirical distribution function of the Shoshone ratios, we should specify the data set from which we should draw, specify the sample size of the new data set, and set the option replace equal to true, because each time we should draw an element from the same data set of Shoshone ratios. Now running this command gives the following new data set of size 20. It consists of some of the ratios from the Shoshone rectangles, and it may be possible that some Shoshone ratios appear multiple times. Here is another new data set of size 20 drawn from the empirical distribution function. A different data set of values, but again consisting of Shoshone ratios with some ratios appearing multiple times. Now there's one last thing we have to settle before we can describe the resampling scheme. Now that we know how to generate a new data set from the empirical distribution function, how are we going to use it to compute a new realization of the studentized mean? In particular, what should we take for mu hat? Now, since mu is the expectation of the random variables xi with distribution function capital F, the parameter mu hat should be the expectation of the distribution from which we have generated the new dataset. Therefore, for the new realization of the studentized mean, the parameter mu hat should be the expectation of the discrete random variable that corresponds to the empirical distribution function. This is a random variable, x star, that has possible values, the Shoshone ratios with equal probability 1 over n. And therefore, its expectation is equal to the summation of the Shoshone ratios multiplied by their probability 1 over n. And this is equal to the sample mean of the Shoshone ratios. Hence, for each new dataset, the new realization of the studentized sample mean is given by the following ratio. Now this brings us to the following resampling scheme for the studentized mean. Generate a new dataset from the empirical distribution function, compute the new value for the studentized mean, and repeat steps 1 and 2 a lot of times. Well, we chose to do 1 million repetitions, and here is the histogram of the 1 million studentized mean values. Now let us return to testing the null hypothesis that mu is equal to the golden ratio 0.618 against the alternative that it is greater. For the Shoshone ratios, we found 2.053 as the value of the test statistic. The p-value is this right-sided tail probability computed under the null hypothesis. Now, the distribution of the test statistic under the null hypothesis is the same as that of the studentized mean. Therefore, we can use the 1 million studentized mean values to approximate the p-value by computing the proportional values greater than or equal to 2.053. And this time we find about 0.0071. Now this p-value is so small that we can reject the null hypothesis and conclude that the Shoshone height-width ratio is greater than the golden ratio. Now of course, the histogram that we obtained as a result of the resampling scheme is an approximation of the true density of the studentized mean. Now recall that if we would have assumed that the Shoshone ratios are normally distributed, then the studentized mean would have a t-distribution. Now when we scale the histogram to having area 1 under the curve, we can compare it to the density of the t-distribution. Now clearly, the histogram is much more skewed to the left. And this also affects the p-value for the null hypothesis that mu is equal to the golden ratio. Now this is more clear if we zoom in around the value 2.053. The p-value computed from the t-distribution is 0.027, about 4 times higher. Now the situation is the same if we approximate the distribution of the studentized mean by a standard normal distribution as a consequence of the central limit theory. The p-value computed from the standard normal is 0.0200, about 3 times higher. And the sample size of 20 is simply too small for a large sample approximation. Now the resampling scheme to approximate the distribution of the studentized mean is also called the bootstrap. Now because under the null hypothesis we generated the new datasets from the empirical distribution function corresponding to the dataset, it is called the empirical bootstrap. Now this brings us to the end of this video. See you at the next video.